So it's our pleasure today to welcome Justin Pearson, who will tell us about constraint programming, propagation, and Galois connections. Justin, please, it's a pleasure to have you here.
Okay, thank you. So, yeah, I'm sort of enjoying the rain. It reminds me of my childhood. Holidays in Wales were basically like this. This was my summers when I was a child. So Jakob said I shouldn't give a too technical talk or too nerdy mathematical talk. So I'm going to talk a bit about constraint programming, which some of you know, but it's also a sort of a particular view I have of constraint solving. Then I'm going to talk a bit about propagation and propagators. So this is the secret sauce of constraint programming. So Pascal van Hendrik, whenever you write a paper with him, you always ask him, what's the secret sauce? What's the so this is the secret sauce. So all this bit will be sort of fairly explained in some detail with nice examples. So this goes on until 3, doesn't it? No, how long?
Yeah, give or take.
So slightly less. I'm not going to talk for an hour. So then I'll talk a bit about an ongoing project, but in not so much detail, about using mathematics to work out what constraint solvers should do. So this partly relates to work that Jakob has been doing. So designing a constraint solver is a sort of hard thing, and knowing what your code should do is a good thing. So I'll explain that as we go on. Okay, so this is where we live. Okay, so as that's actually special platform run. So combinatorial optimization. So we want to solve problems, and if we're lucky, almost all the problems you want to solve are NP hard. Okay, so you want to solve a scheduling problem, you want to solve graph covering, all these things are NP hard. So this slide, I sometimes have to talk to people from, we have a big veterans numerical analysis group. So combinatorial problems are difficult because our domains are non-continuous, they're discrete. They're weirdly nonlinear in a weird way, and then we can't just do gradient descent to find a solution. And the problem with combinatorial problems is that making decisions early on, it's very easy to make bad decisions, and it takes a long time to work out this was a bad idea. Okay, so this is the real world. Okay, so this is SAT. This is a good example of a combinatorial problem. So you want to find this formula is true, find a satisfying assignment, and in some sense, because this problem's in NP, so this is not exactly true, but I mean all the best known algorithms in the worst case have to do some sort of brute forcing. Okay, so if we had an efficient polynomial sum algorithm, then there's $1 million prize. So if yeah, this is NP hard. So basically, it says that if you find a polynomial time algorithm, either you're very clever or you made a mistake. Not finding a polynomial time algorithm is basically just means you're as stupid as everybody else. And so, most NP hard problems are as hard as each other. So this sort of means that there's no silver bullet or free lunch or stuff. So, so what does this mean? So if you're a theoretician, you like proving theorems, you have some paradigm, you're working on SAT or pseudo-Boolean or whatever, and you can prove theorems, you can implement solvers. You all have the secret goal. I mean, this is how we start when we're young, we start doing theory and we say, I know that I'm not a genius, but maybe I'll suddenly stumble on this proof that P is not equal NP. So this is a good secret, I hope. But I mean, you try and push the boundaries of what current techniques to achieve, and this is all the easy stuff has been done. So basically, you have to start talking to people in other areas to find sort of new tricks, new things to prove. So I mean, as a theoretician, so we know that all these SAT and MIP and whatever, they're all in some sense equivalent. But in your chosen area, you can make progress, do nice theorems, do nice stuff, learn from other areas. The other side of the NP hard world that we live in is that you can try and build industrial strength solvers. So you want to solve scheduling problems. So you build solvers that work on industrial size instances, and you make these things robust. And you hope that the problems that you're trying to solve, these fit in the niche where your technique works well. Okay, so the no free lunch sort of says that the no free lunch sort of idea says that no technique is sort of going to be any better than the others in the worst case, but somehow they all have their strengths and weaknesses, and the type of problems you want to solve, maybe our technology is good for that. And then put this on to make your head of department happy. But so theoretical research, derives optimization in industrial strength solvers. So some ideas are useful, some ideas are not useful, but you go to sort of CP conferences or SAT conferences or whatever, and they send spies to find out what you're doing and go and implement the stuff. So theory is all great. So it's so there's lots of sort of solving technologies out there. So SAT solvers. Okay, so these are now cool to use again. So clause learning, that's sort of in some sense made SAT solvers more useful again. So according to Knuth in his chapter on SAT, so he says that clause learning was discovered in the 70s, but they thought it was too impractical to ever implement. He has some argument that some PhD student of Cook actually came up with the idea. Okay, it's somewhere in a footnote in the Knuth volume. But he said back then no one thought it would ever be useful because. So SAT, this is great. It's been a recent life. So mixed integer programming. So companies like IBM and Galois make a lot of money selling solvers that solve problems that are linear equations over where some of the variables are integers. So I mean, this vehicle routing, aircraft scheduling. So there's a company in Gothenburg that does tail planning. Is and when you plan aircraft fleets, you want to first of all you plan the schedule, the routes, and then you have an aircraft fleet, and you plan sort of which aircrafts are going to appear at which airports. So that's tail planning, because the tail is identification, and then you plan which crews go on it. There's a company down in Gothenburg where they use lots of MIP and CP to do this for most of the world. So what I'm going to talk about mostly, so this is what my research has been for the past too long, 25 years, 20 years, constraint programming. So G-code is sort of developed in Sweden by Christian Schulte, who passed away a couple of years ago. IBM has a constraint programming solver. So if you download the academic version of IBM CPlex, it comes with a nice sort of ID and things, and there's a constraint solver in there. The reason why IBM well, they didn't develop a constraint solver, they bought a company, was because if you're doing business rules, if you're doing, so companies want these sort of engines where you can sort of say, if these things happen, then this thing should happen. So these business rules are done as a constraint solver. And, okay, so what is constraint programming? So constraint programming is sort of two things. So this is the other thing about working with Pascal over the years is that he likes slogans. So this is the slogan of CP. So the slogan of CP is that constraint programming is modeling and search. So the sort of thing that makes constraint programming tick is that we have a high-level language, and I'll get to what this looks like in a minute, or a high-level library. So you model the problem with a sort of quite a high level of abstraction, and once you have that problem, then sort of the same level of abstraction, at least until recently, you sort of try and encourage the solver to search in a way that's going to make your problem. You encourage the search to sort of. If you encourage the search in the right direction, then your problem gets solved much easier. So I mean, you know, there's a trivial theorem which is sort of has lots of consequences. So the trivial theorem is that if you know if your problem has a solution, then there's a backtrack-free way of finding the solution. Just make the right decisions and find the solution. So the reason why we spend so much time thinking about search is that we don't know what the solution is, but finding good search heuristics is sort of trying to sort of encourage the solver to sort of make the right decisions to go down there. And so one of the differences of CP sort of against the MIP, so MIP and SAS. So when you do mixed integer programming, I mean there are people who do whole PhDs on just about how do I encode this particular problem in MIP? And you say, well, I can sort of have these sort of triple index variables, like these big M constraints, and modeling is important there. But in CP, you sort of the way the constraints look, and I'll give you an example in a minute. Modeling is important, but you sort of model in a different way. Okay, so here's a nice constraint problem. So this used to be wine tasting, but I've made it more politically correct. So so this is organized by the Swedish Tourist Board. So we want to sort of find judge all these towns in Sweden for their touristic values. So you want to make sure they have proper Swedish fika and nice views. So there's all these beer places. But you have a judge, and the Swedish Tourist Board only has limited money, so you want some fairness constraints. So you want that every judge, every town has 3 independent judges, and you want to make sure the judges have an equal travel load, so every judge does visit 3 towns, but you also want the constraint that so to get some sense that this comparison is fair, every pair of towns like Sigtuna and Lund, every pair of towns, there must be 1 person that judges both. Okay, so here's a solution. So if you look down the columns, Eva visits 3 places, and Leo visits 3 places, and Lund is judged by 3 people, and Falun is judged by 3 people, and for example, Falun and Lund are judged by the same person. They're judged by the same personnel. So if you pick any pair of the towns like Västerås and Sigtuna, there's 1 person that judges both. Okay, so So I mean, these constraints aren't arbitrary. So this example is so if you do statistics, so if you go when you're testing sort of new crops and fertilizers and stuff, so these sort of statistical designs are quite important because then you can draw statistical conclusions from results of the experiment. So this is a model of this thing. So I got a number of towns, and I got a number of judges, and to make the code look easier, I have these ranges. So towns and judges are indexed by integers up to the number of towns and number of judges. I go to jury size, so this is our 3, and I've got a travel load, and I got the fairness, and this is the thing that I'm trying to solve. I'm trying to find an array indexed by towns and judges of 0, 1 variables, subject to a bunch of constraints down here. Okay, so for example, this constraint here says that for every row in the table, so this constraint here is sort of saying that every column, they're exactly 3 judges. It says that every row, they're exactly 3 judges, and this fairness constraint, so this is one way of doing it. So if we take 2 arbitrary rows, since there's 0, 1 variables, if we take the dot product and sum, so take the dot product and sum of things, that should equal the fairness number. Okay, so this is one way of modeling this thing. This is another way of modeling it. So we can do this with sets. Each town has a set of judges. You have the same constraints, and then you can write a model like this. So we want the cardinality of the set of judges to be a certain value. This is working out the trouble load, and then this rather ugly thing is just set into a section. Okay, so this is one way of modeling these things. So I mean, incidentally, if you want to solve these problems, so I mean, these models work really well for small values. If you're solving big things, you need to do symmetry breaking and all sorts of weird stuff. So this is a dangerous example because, well, this is a good example because everyone understands Sudoku problems. This is a bad example because sometimes I give well, lighter versions of this talk to management, and then they go away thinking that constraint programming is just sort of people solving logic problems in newspapers. So this is both. So if you're talking to university management people, this is a dangerous example. If they understand it too much, they think it's simple. So you must make sure that they think they understand things, but not quite enough. So you have an array of values. So how you populate the values with the clues is incidental. But here we have the sort of the new thing with constraints. We assert that each column, each row, and each subsquare, we assert that all the values in that row, column, or subsquare, that they're all different. Okay. So I mean, the good thing about being a computer scientist and doing constraint programming or something is that. So I used to have some stepchildren. I still do, but I mean, when they were young, they always accused me of cheating because I'd get some problem in the magazine and I just sort of code this up and do the solution. For them, this was cheating. But so if you look at Sudoku, so you can buy Sudoku books in strategy books that sort of tell you all these wonderful tricks. And And there's quite a lot of mathematics in there, but it's all sort of hidden bizarre tricks. These constraints, such as all different, or taking the sum of some value, saying that the sum of some set should equal a value. These constraints, these are what constraint programmers call global constraints. So logically, they're equivalent to some decomposition. So I'll get to that in a minute. But in some sense, these are sort of what makes constraint programming tick. So one of the problems of learning constraint programming. So, I mean, if you want to write a Stocker model, then, and if you want something that sort of works well with large Sudokus, then you have to use this all different constraint. So if you work in constraint programming, then when you're doing modeling, part of using constraint programming well is sort of understanding that you have some constraint unit expressed, and it's actually some global constraint in the solver already. Okay, so and this is another slogan. So in some sense, global constraints are there to sort of capture combinatorial substructures that keep appearing. So this is an advert. So all this code that I've put in the slides, well, this model, this is real stuff. So this is not fantasy. So this is there's a language out there called Minizinc, and Minizinc looks like this. So this is a part of a Minizinc model. With a little bit at the top, it works well. So the Minizinc language, you can go and download it for free. It's got one modeling language, and then and it's got bunches of backends, so you can talk to constraint solvers, you can talk to MIP solvers, all sorts of things. And if you look at the Minizinc library, there's a large library of global constraints. And some of the solvers implement these global constraints, and some of them don't. But when it doesn't, then it does a reformulation. So this is, this is the big thing about constraint programming. Modeling is a really big deal. Finding a good model has a drastic effect on your solving time. So when you're doing, when you're doing SAT, I mean, modeling is a big deal, but people spend effort making SAT solvers intelligent that bad models work well. But when you're doing constraint programming, we also spend time making efforts so that bad models work well. But because you have these sort of high-level global constraints, there's sort of less reformulating things into equivalent things that are easy to solve is much harder. The onus is sort of on the model. Okay, so this is again the sort of way that people think about how you design constraint solvers. So one idea. So essentially, when you have a constraint solver, you're trying to represent the set of all solutions, and you want to sort of take your constraints and find out what subset of the solutions are actually still valid. So maybe you come up with the fact that there's no solution, or maybe you say, well, the solution late, or you might want to say that this is a solution to your problem. And there are various techniques. So one idea, for example, is for each variable to keep track of the lower and upper bounds of values. Another idea is for each variable to keep track of the set of possible values that it can take. And then, well, just there. So one thing, big area in constraint programming for a long time was actually, if you want to write constraints over sets, then can you think of a way of representing possible sets that can take part as solutions? Or if you have constraints over strings, can you work out whether a representation is a string variable? So because people write bad, so JavaScript is great for research. So people write web pages, and bad JavaScript is really bad. And a common thing to do is take a string that the user gives you and then just feed it straight into some database. And, there are all sorts of wonderful cross-site scripting attacks because people write bad codes. So there's a whole benchmarks of this is big in the formal methods community, but there's some working constraints as well. So if I got some representation of what happens to strings in a JavaScript program, a cross-site scripting attack is finding a solution that allows you to insert a bad string into somewhere. So analyzing bad JavaScript. So there's some working constraint programs. Okay, so so how does a constraint solver work? So I'll explain this in more detail in a minute. So basically, a constraint solver does two things. It does a step called propagation. So somehow we use these global constraints. So let's do an example. So a Sudoku thing. So so this is a rather trivial thing. So for example, this top square, this top right-hand square, top left hand, whatever, top square, right or left. That square there, we know that it can't be 6 because the values in all rows must be different, and we know that it can't be 2, and we know that it can't be 8. So when we start off with this domain, you can take any value, and then we use the constraints we have to remove possible values. And the way you solve Sudoku problems is that they're set up in such a way that you sort of do this elimination, and eventually you find that some square has to take a value, and then you keep repeating the loop. So my relations call me cruel. So one year I wrote a program that generated Sudoku problems that you could almost solve. So they're almost solved, except at the end you get a contradiction. So I generated some of these problems to give to my relations. If you want to waste time solving Sudoku, you deserve everything. So propagation, we use global constraints to remove values that can't take part in solutions. And then, sort of unlike most Sudoku problems, then we get to a state where we know more, but we don't know enough. So we have to search. You have to make a choice. You have to say, well, let's imagine this square is the value 9. And then you live with the consequences, and either you find a solution, or you say, well, that's a contradiction, so let's try the value 8. Okay, so search and propagation and interleaved. So this is all good. So let's go back to Sudoku. So this is all different. Okay, so this is all different on 4 variables, A, B, C, and D. So logically, this is equivalent to n squared binary constraints. Okay, so logically, these two things are the same. But the point is that with global constraints, we can if we sort of consider all the constraints at the same time, then we can do more reasoning. So if you look at these domains, if we know that A belongs to 4 and 5, and B belongs to 4 and 5, C belongs to 3 and 4, and D is 1, 2, 3, 4, 5. Because A and B belong to 4 and 5, this means that so A and B must take a value. So this means that we can strike out 4 and 5 from this domain here. And then because we've used the value 4 and 5 here, then again we can strike out the value 4 from here, so that we know that C must be 3 and D belongs to 1 or 2. But the point is that if you just consider these binary constraints separately, so when you have a binary constraint that A is not equal to B, okay, so if you look at here, so A is not equal to B, this doesn't do any work because if I set A to 4, then I can set B to 5. If I set B to 5, I can set A to 4. So on its own, these n squared constraints, they can do some work, but they can't do this work of the global reason. So global constraints, they're a big deal because they come with these propagators, and they come with relatively efficient propagators. And the reason why you want to use your global constraints when you're doing constraint programming is that you want to use these efficient algorithms to do this sort of global reasoning, these 4 variables. So this is what we teach the students in Uppsala when we do global constraints. So there's an efficient algorithm out there. You build a graph. On the one side you have all the variables. On the other side you have the values, and you draw edges in them. Edges between variables and values if they're in the domains. Then the observation is that a solution to this all different constraint is a maximum matching in the graph. And if you're awake in your sum course, then you know that there's an efficient way of finding maximal matchings. And then once you've found the maximal matchings, then you can there's also an efficient algorithm that tells you the edges that once you found one maximal matching, there's an efficient way of deciding which edges can belong to any matching. And then once you've done that, then you can just prune away. You know which edges can't participate in any maximal matching, and those values you prune away. So then you sort of get to this step. So this is so if you do graph theory, so there's these are standard algorithms. So this was a big deal in the 90s, constraint programming, when they found this algorithm. And Rajan was sort of trying to find an algorithm to do this. He thought there must be one. And apparently one of his colleagues had Claude Berger's book on graph theory open on his desk, and he was actually reading the chapter on maximal matchings, but they took a long time to make the connection. So the good old days of constraint programming is you could invent some new global constraint, and then you could go and raid all the mathematics textbooks and look at the algorithms, and you could find some algorithm mathematics textbook. You could implement this stuff and say, hey, I've got a new fancy propagator. Here's my paper at the conference. Doesn't happen so often now. So this is sort of part of the. So the point is that modeling, you want global constraints. You want global constraints because they come with propagators, and if you have a propagator, you have to implement the stuff, and if you actually try and implement this algorithm efficiently and correctly, this is a non-trivial. I mean, it's not hard, but it's a non-trivial piece of code. So, a 1,000 lines or out on it. I mean, to do this properly, it takes time. It's one of those problems where you think, oh, it can't be hard to implement, and then a month later you're still sort of finding bugs in your code. So when people design constraint solvers, so implementing global constraints is a big deal. Implementing global constraints is a big deal. And so, for example, both Matt Carlson with Sixtus and Christian used to do this with G-code. One strategy when you build a constraint solver is to use lots of random testing. So you have a dumb thing, dumb but correct implementation that sort of works out what propagation should happen. You have your fancy global constraint, and then you just generate random domains and see whether it actually does the right propagation. And this is a good way of finding bugs. When I used to teach the testing course, never underestimate the power of random number generators. Okay, so this is sort of so now it gets a bit vague in the maths. So I can explain a bit, but not too much. A few years ago, more than a few years ago now, so one of my PhD students was we were trying to do these these string constraints. So we were building a constraint solver, and we wanted strings, and we didn't know what the lengths were. We wanted to be efficient with the memory. We needed some internal data type that was growing and shrinking. We had to keep track of sort of some positions in the string we knew what the values were, some positions in the string we had no idea, some positions we had potentially they could be in sort of certain sets. So we implemented some complicated propagator. And the sort of question is, what should this propagator do on these domain representations? So if you go back to all different, you can sort of write a formal definition. You can say, well, a value, like the value 2, is allowed to be in the domain because I can find some solution to this constraint where the variable d takes the value 2. And for example, the value 5 can't be in variable d because there's no solution where d can take the value 5, because this thing over here said a and b, they've sort of sucked up all the value. They have to use 4 or 5, so it's not available. So this is called generalized arc consistency. But when you sort of have these complicated domains, you sort of have to ask the question, what should the propagator do? So I'm lazy, so there are two things it can do. So one thing is you think hard and you have lots of cases and lots of case analysis and stuff. Then there's lots of writing and I get lost. Or the other thing is you use mathematics to actually help us. Okay, so the typesetting wrong. Okay, so yeah, so the way we think about it is I know what it is. So the way we think about it is we sort of think about what the constraint solver is doing. So this is back to generalized arc consistency. So somehow a solution is a mapping from variables to values. So this array in the Sudoku, this is a 9 by 9 set of variables, 81 variables, and each take values from 1 to 9. But when you build a constraint solver, so one way to build a constraint solver is you just somehow maintain what the upper and lower bounds on the variable are going to be. So if you're doing some sort of optimization problem, it's not. good idea. Or the other way is you sort of say for each variable, so I'll correct the typeset. For each variable, what values can it satisfy? What values can it be? So going back to the Sudoku thing here, so this is saying that A can be can take the value 4 or 5. Okay, so and the sort of mathematics, I mean, is to sort of think about the relationship between this sort of real world, or point of view, but this sort of this set of solutions, and then we have this representation. We try and think about how these things match up. So let's do an example. So suppose I picked a notation. My set of solutions for a problem, so this is some constraint. So it has two assignments. I say x can be 1 and y can be 1, or I say x can be 2 and y can be 3. So since I wrote these on the train, let's see if I actually got them right. And if I look at the bounds of x, so x can take a minimum value 1 and a maximum value 2. And then y can take the minimum value 1 and the maximum value 3. So in our bounds representation, this setup here would be represented by this over approximation. So this original thing only had 2 solutions, but this thing here, so so the minimum value of y is 1 and the maximum value is 3. I haven't outlawed the value 2 for y. And then in the sort of the domain representation, there I can actually say more. I can say x can be 1 or 2, and y can be 1 or 3. But again, in some sense, and I'll show you on the next slide, we have more solutions. So the whole of constraint programming, or the mathematics behind constraint programming, is sort of going from this set of solutions to some representation of set of solutions. This map, so this going from the set of solutions to the representation, for various reasons, we call this map out. Okay. And then the other way, so given, for example, the bounds representation here, I can ask, well, if you give me a bounds representation, what are the possible sets of solutions that I can have? And this has this large set, so because it has this cross product, so it has all the possible values. X can be 1 or 2, but y can be 1, 2, or 3. So this has six solutions. Okay, so given my domain representation, I can go back and say, well, what's this in terms of set of solutions? And this map is called gamma. Now, it turns out that mathematicians and computer scientists have been studying this for years. So if you have a pair of maps, and I'm not going to prove. If you work out what these maps alpha and gamma should be, then they satisfy a very special condition, which is called a Galois connection. And essentially, this condition is asserting that the alpha map works out the abstraction, and the gamma map is the map that takes the abstraction back to the set of solutions. And this condition means that the alpha map is the one that gives you the best representation. So this is called a Galois connection, and people have been studying it for a long time. And the reason why this is fun is not so you can prove theorems, but basically that it comes with a lot of free mathematics, and this makes sort of developing propagators rather pleasant. So there are lots of things you can prove free. So, for example, you want propagators to be well behaved. You want them to throw away information, not add information. You want them to not throw away things that should satisfy the constraints. This sort of in most cases, this is the correct abstraction. So, yeah, this is the one slide. Things this is part of what I'm talking to Jakob about last couple of days. So, basically, what it says is that let's find the example again. When you're implementing the propagators, you're implementing on this abstract representation, the domains. But when you specify them mathematically, you're sort of specifying a constraint as a sort of set of solutions that satisfies some condition. So this is not a very good example, but you know, the set of things where all the values are different. So you do the mathematics in this board on the set of solutions, and then you use the Galois connection to sort of tell you what this should be like in your domain representation. So mathematically, it gives you a specification for sort of the different domain representations. And then, so when we were doing the string constraints, so this was actually true for free. So we actually had a lot of quite complicated constraints, which because we'd set the theory up in such a way that we actually got a whole bunch of propagators for free. And actually, the derivations we had are almost actually, I mean, there's almost a one-to, so they're almost one-to-one correspondence with code. So it's a certain type of style of propagator design, and we actually got code out of this. And then this is also part of the native clause solvers. So that's the theory, which is a very sketch. This is an advert. So I also spent two summers ago. It was seems every summer now. At least 2 summers ago, I couldn't go sailing because it was raining too much, so I was stuck in the caravan. My wife was doing something else, so Microsoft has a theorem prover called Lean. So it's based on dependent type theory. And the nice thing about Lean is that it comes with lots and lots of non-trivial mathematics. So I'll show you an example if you want to it. And because the other thing about Lean is because it uses Unicode, when you write Lean, it looks like mathematics. So you say alpha, you know, F is a right arrow, and you actually write things. So if you're proving things in other theorem provers, you sort of have to have all these macros and stuff. You write stuff that looks like mathematics. And at least if you're doing sort of the sort of type of equational reasoning that you end up doing in certain areas of mathematics, with some practice, it's actually not much overhead from paper and pencil proofs. And the reason why this was so, this is what so maybe I'm a bad mathematician, maybe Jakob is a much better mathematician than me, but I'm very good at convincing myself that things are true. And part of this is this theory of propagators is that so the archetypal, so the example I showed you is you have a power set of set of solutions, and you have this domain representation, but you want this to apply to sort of lots of different representations. So you sort of relax assumptions, and I'm sort of very good at convincing myself that obvious things are obviously true because they're so obvious. I can't be bothered to write out the proof. And at least when you set up enough machinery, sort of things that should be obviously true, that should be easy to prove. The tactics, if you set up enough groundwork, it's not going to be hard to prove that in lean. So if you can't convince the theorem prover that some obviously true fact is obviously true, it's probably not true. And so, I mean, I really like to find out the things that I believe to be true or false much earlier than later. So yeah, I mean, it's little advert for lean. So try lean. These things. So one nice thing, well, one complicated thing about lean is if you Google for lean, then you get to Microsoft's webpage. But the real web page you want to get to is the community edition. So if you Google lean community edition, then you get to stuff. So questions.
You. So how much, I got curious about lean. So
Yeah.
how much math do you think we should do in lean? I mean, if we're doing complexity theory, should we like do our lower bounds for proof systems and formalize them in lean? Or?
So actually the problem, so it's good at doing sort of maths, but when you start doing structure, so when you have proof systems, you sort of want to do structure inductions over sort of trees and stuff, and it's not so good at that at the moment. So that I mean that involves sort of basically I mean it's not impossible. You can represent terms and stuff and show derivations and all this stuff, and people have done some stuff based on that, but the automatic tactics that sort of kick in don't kick in very well for the structure induction stuff. So if the first thing you want to prove that something reduces to a lower bound, this will probably put you off the system for life. You have to develop more tactics. So the problem with structure induction. So yeah, so some of it's actually quite easy. So you sort of represent terms in the language, and you sort of talk about reductions, and you want to prove two terms are equivalent. It sort of works a lot of time, but if you want to sort of talk about, you end up in, it's a bit of software engineering how to represent these things well. And I think the reason why this hasn't, because it's mostly mathematicians working on the library, and they're not so good at software engineering, sort of engineering stuff. But it is certainly possible. So I wouldn't try it for the first proof. Yep.
And how does it compare with Mathematica?
Well, Mathematica is just for I mean, Mathematica just sort of solves things for you. I mean, it doesn't. There's no sense that Mathematica is not even correct. I mean, it gets integration wrong all the time. I mean, you can make it get integration wrong. I mean, it works well. I mean, Mathematica just you ask it to integrate something, most of the time it's correct, or you ask it to calculate something, it gives you the answer. There's no guarantee of correctness.
And then I can ask Lean a question and ask it to present.
No, in Lean you'd have to. So Lean is a different strategy. So in Lean you'd have to prove things. I mean, Lean is a tool for writing proofs.
But I need to write the proof.
Yeah.
Check.
Yeah. So for example, okay, this is a very trivial proof, and this is written in R. So you don't need to worry about it. So I basically wanted to prove that so this is an example of trivial proof. So I have a fact that that some composition of some function it satisfies this condition. So for any x, if I apply g of f to x, it's less than or equal to f of x. Okay, and then I have a sort of proof that I have this fact that f of x is less than x. So this is a really trivial thing. I wanted to prove that this g of f of x is less than this value x. Okay, so this is basically true by transitivity. Okay, so this proof is, I mean, a lot of lean code is a bit sort of long-winded, but one style of proving things in lean is sort of Now let's find another example.
Where can we see what the theorem is that you're proving?
Yeah, because I put it in a the problem was there's a macro in there which actually, so I'll try and find one which has a statement, but okay, so here's a trivial thing. Okay, so if, for example, I know, so this is what I'm trying to prove, this statement here. So given some conditions on F, if I have some element X that's an atom, then either F of X is equal to X or it's equal to the bottom of the lattice. So that's the thing I'm trying to prove. Okay. This statement up here, so these statements here, so this is one of the preconditions, which I'll unwrap in a minute, but this is a precondition of proof. This is this is just asserting that I got a function. This is a bit like Haskell type classes. So I've got a type, and I'm asserting that that type is a partial order, and it's a partial order with the bottom element. So there's a one-line proof of this, but this fact here, so I can say have, I can temporarily introduce fact. So I introduce this fact that f of x is less than or equal to x, and this fact comes from the assumption that we made. And then the proof is the proof uses previous proofs, but once you have these facts, then basically you can sort of you end up just combining the facts. So, this is the great thing about lean is this is probably not going to work. Is it has this function called so I mean it has this function called library search, which searches the whole of the mathematics library, also searches what you've proved already, and tells you a term that can prove this. So one style of proving things in lean is sort of coming up with elementary facts and then sort of firing off the library search to actually find out whether it can actually, because it's a typed language, to find out whether it can sort of find a theorem in the mathematics library or a theorem you prove that actually gives you the proof term that you're looking for. So Isabel has a similar thing. Isabel has this thing called sledgehammer, which I never got working. This works sort of well. So apparently you can use this with Visual Code, but I don't ever use Visual Code. Emacs is the only editor that.
I hear that if you use Visual Studio, it puts like nice emojis when it finds the right things.
This about sums up sort of the market for Visual Studio users. I mean, the Emacs flashing cursor should be enough to make you happy. If you need emojis, then definitely.
Very nice, and like it fails, like it shows you like the sad face, like what. It's like a confetti going off. Like, oh, I found it. It turns math into a game guy.
Yeah, I mean, actually, so this is this is a good point. I mean, maths is a creative thing, but I mean, a lot of maths is actually just grinding away trying to prove sort of stuff, and you can prove theorems while watching television. You know, you just keep applying random stuff, and then eventually sort of find a combination, and then later on you tidy up the proof when you're not watching TV. But summer maths is just sort of finding lemmas and stuff, but then doing some grunt work to prove these lemmas. But that stuff is sort of, and I think machines will replace this stuff. I mean, I think mathematicians won't replace, but I think a lot of this trying lots of tactics and stuff. This will get more powerful. Machines will just prove all these trivial things, well, less trivial things. And our job would be to come up with nice lemmas, combine them and stuff. But
Okay, any questions from the virtual audience? Or any more questions from or comments from the physical audience?
What's Mikhail? He's everywhere.
So otherwise, I guess we can thank Justin again.